Our next section is related rates, which is an important class of calculus problems. So this is the kind of question you have. We'll think about this question just to start with. A fire spreads across a prairie with no wind and a uniform distribution of fuel. The fire burns outward in a circle whose radius expands at a rate of 2 meters per minute. So one thing I want to start with is just sort of a general discussion about how we do applied problems in mathematics, because this situation seems really artificial, because if you're really studying the spread of a fire, there's going to be wind, there's going to be terrain, there's going to be different fuels in different places. The problem's going to be much more complex. So what we do in mathematics is we start by studying simpler examples, and then once we really understand how that simpler example works, then we can add in all the confounding factors of the wind and the terrain and the different types of fuel and so forth. So we start with an idealized version of the problem. So that's similar to how in physics you start studying trajectories and you neglect air resistance, right? Well, if you actually do ballistics work and you neglect air resistance, you're going to get everything wrong. But you have to start with the simpler problem where you neglect the air resistance. So I just wanted to make a note about how this problem is idealized, but studying idealized problems is what allows you to have the tools to study a more realistic and complex problem. But still, it's a decent sort of idea. So we want to know at what rate is the area of the fire expanding when t equals 10 minutes and when t equals 20 minutes. Now, the radius is expanding at I should have said a constant rate. I mean, it's sort of implied in the fact that it's just 2. A constant rate of 2 meters per minute. All right, so the radius is expanding at a constant rate. So here's my brush fire, and it's burning in a nice circle. And it's expanding outward because essentially the fire burns at a certain constant rate, and it's going to do that in every direction. It's going to burn at a constant rate. I mean, you could think of a spreading light wave or sound wave, anything. So as the radius is expanding at a rate of 2 meters per minute, okay, the radius is expanding at 2 meters per minute. How is the area changing at that moment at t equals 10 minutes? And is that going to be different from 10 minutes later when our fire is bigger, all right, when we have t equals 20 minutes, the radius is still expanding at 2 meters per minute. Is the area expanding at the same rate or a different rate? That's number one question. So I have the radius is getting larger at a constant rate. Is the area expanding the same rate? The area covered is expanding rate the same rate in both cases at t equals 10 minutes and t equals 20 minutes. Well, it's not. It's not. The area is not expanding constant rate. So the radius is expanding at a constant rate, but the area is not. So here's how we handle questions like this. We start with an equation that relates the radius and the area, right? So I know that the area is equal to pi r squared. Now, this is the relationship of two variables, but this question is really about when the radius expands at a certain rate, at what rate is the area expanding? So I'm comparing two rates of two variables that are related. Hence, related rates. All right, now how you do it, once you get the equation set up, which as in optimization, that's kind of the problem, but how you handle it after that is fairly straightforward. So what we're going to do is take a derivative, because it's calculus, and so far that's the only calculus-y thing we know how to do, is take a derivative. But we're not going to take the derivative with respect to r, right? If I do the derivative of this, it's just 2 pi r. But I don't want the derivative with respect to the radius. I want the derivative with respect to time. So I'm going to take, because that's the rate of change, I want the rate of change of area in time, right? Think about the rate of change of the area is in distance units per time unit, all right? This is distance, this is time. The area is going to be A, and when I say how fast is it expanding, I mean in time, right? I guess at what rate in time is the area expanding. So instead of doing the derivative with respect to r, I'm going to do the derivative with respect to t. All right, and then what I get is, so the derivative of a with respect to t, I just say that's dA dt. Now, when I go to do the derivative of r with respect to t, r is part of a function. So what's really going on here is a chain rule. The pi is a constant, I can just bring it down. The derivative of r squared is 2r, but r is a function of t. So what's implied in here is this is really r of t, and this is really a of t, right? So when I do derivative a of t, I get dA dt. But when I do this derivative of pi r squared, I'm going to get pi times 2r. But then I'm going to have times dr dt, because this r is really an inside function. The a doesn't have that problem. It's not inside another function. If this were a squared, I would have 2a dA dt. Really, you could think the derivative of a is 1, and then times dA dt for the chain rule. You could think of it that way. All right. So this is an equation that I have, and what I have now is an equation that relates the two rates. So this is an equation that relates two variables. So this relates the variables. And this equation relates the rates. All right, now we'll talk about what to do with it in the next video.